This problem is called combination sum and it's version 3 of this problem. And here we are given two parameters. One is n, the second one is k. So we have to form a sum of n using k values, exactly k values. And these k values has to be from 1 to 9 only. And n will be accordingly not too large, because if n is very large, then you cannot combine k variables whose value is between 1 and 9 to make n. And here also duplication is not allowed. So all the k values from 1 to 9 has to be unique. So you see, even if you add all the values, let's say best case can be k is 9 since there is no duplicate. So even if you take all of those, you can form 9 multiplied by 10 by 2, that is 45. So you cannot form more than 45. So let's see an example. So let's say we are supposed to use 3 variables, that is 3 values out of 1 to 9, both inclusive, and no duplicates, and total sum should be 9. So how can we form 9 using 3 values? Let's say first value is 1, then we have 2 values left, and using these we have to make 8. Let's say next value is 2, we cannot have 1, so 1 we have used, so we have to start from 2 to 9. So let's say next value is 2. Now we have formed 3, remaining value is 6, so put 6 here. So this is a valid possibility, but we have to write all such possibilities. So even if we have got one solution, and this will be the probably smallest solution since we are starting from 1 for the smallest possible value for each place. Next we will do backtracking. So 6 we remove, and then we cannot form 7, 8 or 9. So we go one step back further, and 1 is fixed. In place of 2, let's try 3. Now it's 4, remaining is 5. So put 5 here, and so on. So this is how we would manually do it. And this is exactly how we would do in this solution. And this approach is called, if you remember, backtracking. So in backtracking we exhaustively try out all the possibilities. So here all the possibilities, some possibilities we are eliminating because duplicates are not allowed. So that's why once we take a value, we don't take it again. So what is the approach here? We have k slots, exactly k variables. So first we have to put 1. All the values will be from 1 to 9, no duplicates. So put 1 here. Now our problem reduces. So earlier it was 3, 9. Now it's, so let's take this. So first we put 1 here, the remaining value n reduces here. So n is now 8. 8 is remaining. So whatever is n, we take a value of I, and then n minus I we do. So n is updated to n minus I since I we have included, and I will vary from start to 9. Why start? Because we will call it multiple times and start will vary. So once we have put 1 here, we will need to fill 2 places, and start will be 2. We cannot take 1. We have already taken 1. So we will try all the values from 2 to 9. So first possible value will be 2, and then we will pass here start equal to 3 since 1 and 2 we have included. So whatever value we just include, we pass 1 more than that as the start. So there will be some function f which will do the job of backtracking, and it will be recursive. So start will be one variable. 9 we don't need to pass, 9 is always fixed. And what value we want to make, let's call it n. And k will remain constant. It will act as a counter. So we will keep inserting in some temporary vector. So here we inserted 1, then we insert 2. So when this size becomes k, we will use that check. So that's why k is constant. So this is n. So here what we do, if n is 0, that is we don't require any further value, and k is 0, that is we have exactly k elements in this vector. We will also pass a temporary vector, let's call it temp. Then we will insert, this is a valid solution since now the required value is 0 and the required number of variables is also 0. So exactly k values are making exactly n. So this is a valid solution. So we include it and return from it. Otherwise, if n is less than 0, that is we have overshooted. Remember that how do we update it? N minus I. Whatever value we include, we subtract from n. So it may be possible that n becomes negative. So in this case, there is no possible solution. So we return. Otherwise, if n is greater, that is there is some more value required and k is also, and the size of this temp vector is less than k, then we continue. So we will run a loop I equal to start to 9. So in this temp, push this I and then call this function recursively. So start will be I plus 1 and n will be updated to n minus I, since I is now included. So required sum is n minus I, and k remains as usual, and also pass the temp. And if this is called again, so this will be checked in the beginning, and if it satisfies this condition, we will add it to the result. If not, we will return back, and then we will try the next value. So here what we will do, whatever value we had pushed, we will push the next value, but before that we will remove that value, because here we try 3, it does not work. We try 4, it does not work. So we are pushing this value and then popping it to try the next value. So that's why here we will pop temp.pop, and we will continue. So let's again using this approach, let's do a dry run on this k equal to 3, n equal to 9, and we have a temporary variable. We have a global result which is empty. We have not pushed anything, and let's say we call f, and it has a start, it has n, and let's say k is also there, it will not change. Let's keep it here, and then we have a temporary array or vector or list, whatever language you are using. So if this, let's call it temp.size, or better to call it combination, since we are trying the combinations. If temp.size is equal to k, then that means no more variables we can add. So we have to check if n is also 0, then this is a valid solution. Then result dot add this temp and return. What else? If this is not the case, that is temp.size is not equal to k, its size can never be greater than k, since we are starting from 0, and as soon as it reaches k, it will enter this loop and it will return. So it cannot be more than k. You can also add greater than equal to k, but this greater is not required in fact. Otherwise, for I equal to 1, I equal to start, to 9, temp dot push I, then f start plus 1, n minus I, and temp, and then temp dot pop. So I have repeated this thing here. I think we had already discussed it, but we repeated it just to make it more clear. Now we will do a dry run. So we have k equal to 3. So what will happen? It will call f, and this start will be 1 in the beginning, and n will be 9, and this will be empty. So this condition will not satisfy, so we will come here for, this is a start here, I equal to 1 to 9, and this 1 is coming from this temp, insert 1 into it or insert I into it. So this is now 1, and we will call f, start will be 2 now, and n will reduce to 8. We have added 1, f8 and 1. Then this will again come here, it will not satisfy this, so it will again call for I equal to 2 to 9. Then insert 2 into it, so it will become 1, 2, and it will call f. Next start will be 3, and the remaining value will be 8 minus 2, 6, and 1 2 is passed. Again this will check the base this case, but it will not satisfy, so this will call for I equal to 3 to 9. So insert 3 here, so 1 2 3, and then call f 4, and the remaining will be 6 minus 3, that is 3, and 1 2 3. So now it will check that its size is k. So it will check whether n is 0 or not. N is not 0, so it will not insert into the solution and simply return. So now this returns back. So this was not valid, 1 2 3. So what we will do, we will pop. So 3 we had inserted, we will pop 3. Now next value of I will be 4. So we will insert 1 2 4 and call this f. Start will be 5 and n will be 2 this time. Again this is not 0, so it will again return. Next we will pop 4 and insert 5. So it will call on 1 2 5. Again it will not be equal to 0, n will be 1. So this will pop 5 and push 6, 1 2 6, and we will call f on this, n equal to 0, start equal to 7, and this will satisfy this condition, n is 0, so it will insert 1 2 6 into the result. Next we will push 7 here, it will not satisfy, n will be negative, 8 here, n will be negative, 9 here, and 8 n will be negative. So we are exhausted with all the possibilities where first two values are 1 2. So this will terminate, this entire thing will terminate, and we will come here. So let's erase this part is executed completely. And then we will have pop this and push 3. So we have 1 3 now, and then call f, start is 4, n is 5, and this is 1 3. So this is not equal to k, that is 3. So it will again have a loop here for I equal to, you get the idea. So we call f 1 9 empty, this calls f 2 8 1, this thing, then 1 remains constant. We tried all the values of 1 2 and got this solution. Then you will try all the values with 1 3. So 1 3 4, and n will be 1. So we will pop this and try 1 3 5, and this is valid, so we will add it 1 3 5, and then we will try 1 3 6, 1 3 7, 1 3 8, 1 3 9, and none of them will work. So we will come one step back, pop this, and it will be 1 4, and it will be 5. So it's more than 9. Similarly 6 7 8 9 all will be more. We will try with 5 and then pass 6 7 and 8, none of them will work. Similarly 1 6 1 7 1 8 1 9, none of them will work. So we will come back here to the first level. So here we had tried 1, next we will try 2. So first element is 2, and then we will try 2 3 and 4, and it will work, and then none of the other solutions will work. So these are the 3 possibilities. So try with one more example and it would be much more clearer. Now let's write the code for this. So we will write a main function for backtracking. We will call it try combinations. So we pass the combination k, also n, and start, from where to start next. And here what we will do in the main function, so this is empty combination initially, and we will put into it values. And we will start from 1 in the main function, and let's have a result. We can pass by reference, or let's make it member. vector of int. This is the return type. Let's call it result. This is also empty initially. If k equal to combination dot size. So this means there are already k values in this vector. We cannot add any more value. Then better this required sum be 0, then we will add it, otherwise we will simply return. Even if we add, we return. We no longer need to process further. So this is the next start. I we have pushed here, so next it should be I plus 1. So it's pop back. And this works. And the solution is accepted. And if you see the time complexity, it's here. It's on the smaller side. If you try a few times, I am pretty sure it will be here. And it will give 100%. So just we forgot to see the time complexity. What is the time complexity here? So we have to choose k numbers out of n numbers, and n can be, so not this n, so we have 9 values, 1 2 3 4 all the way up to 9, and we have to exactly pick k values from here. So how many ways are there to select k numbers from 9 numbers? It's n choose k. In this case, not to be confused with this n is the required sum. 9 here. 9 is the total number of values. We have to choose k from them, exactly k. So it's 9 factorial divided by k factorial and multiplied by 9 minus k factorial. This is the standard formula for n choose k, here 9. So this is the time complexity. And space, we can keep track of k values combination. So this length is k for one combination vector, but we can have multiple such vectors in the result. So if you count this result also, then some factor times k. So if you take this combination, then it's O of k, or it will also depend on number of solutions we have, so it can vary, but k can be at max 9. So it's a topic of discussion, you can discuss, but let's take it O of k for just the temporary combination thing and not the result. Now let's write the same thing in Java and Python. and the Java solution is also accepted. Finally, we will do it in Python 3. K is not changing, so we can use this K. And make sure to make a copy, otherwise this same combination vector will be updated. So whatever you put here and then you update it, this same thing will be updated, and finally it will become empty. So we will make a copy here. And the Python solution is also accepted.